Imagine, for a quiet moment, that you are drifting outward from the warm blue curve of our planet, past the grey hush of the moon, past the slow orbits of the outer worlds, until even the sun shrinks to a single pale spark behind you. Out here, the silence is enormous. Galaxies hang in the dark like flecks of slow light, each one holding billions of stars, each star turning through space the way a leaf turns on still water. The whole picture looks smooth from this far away. It looks like one calm, continuous thing, stretched gently in every direction. That smoothness is the first language the universe seems to speak. We call it general relativity. It is the language of curves and bends, of space and time woven together into something soft and flowing. It tells us that a star sinks into the fabric of space the way a heavy stone sinks into a blanket. It tells us that light follows the gentle slope. It tells us that time itself slows near a heavy thing, the way honey slows when it pools. In this language, the cosmos is a single quiet sheet, and everything large in it moves like a dancer who has never once stumbled. But the universe seems to speak a second language too, and that one sounds nothing like the first. It is the language of the very small. It is the language of quantum mechanics. Down beneath the level of atoms, things stop being smooth. They flicker, they jump, they appear in more than one place at once, and they only choose where to be when something looks at them. Particles behave like waves. Waves behave like particles. Empty space hums with tiny, restless motion, as though the void itself cannot quite hold still. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. Both of these languages work. That is the strange and beautiful part. General relativity has predicted the bending of starlight, the slow drift of clocks on satellites, the ripples in space we now call gravitational waves. Quantum mechanics has predicted the colors of atoms, the behavior of light in a laser, the patterns inside every silicon chip, in every device you have ever held. Each theory has been tested for more than a century. Each has passed nearly every test we know how to give it. And yet, when we try to make them speak to each other, they fall silent. Or worse, they argue. You can feel the trouble most clearly in two places. The first is the heart of a black hole, where matter is squeezed so tightly that both theories must apply at once, and both throw up their hands. The second is the very first instant of the universe, when everything we see was packed into something smaller than a grain of dust. In those moments, the smooth sheet of space-time and the trembling foam of quantum fields must somehow be the same thing, but no one yet knows how. This is the missing bridge. It is the gap at the center of modern physics, the unfinished sentence in our story of the cosmos. Some thinkers suspect the bridge will be built from tiny vibrating strings, each one humming at a different note to make a different particle. Others suspect space itself is woven from small loops, like a chain mail of geometry too fine to see. Others wonder if gravity is not really a force at all, but something that emerges from deeper rules we have not yet uncovered. Each idea is patient, each idea is partial. None has yet been confirmed. What we know is this: the universe is consistent with itself. It does not contradict itself when no one is watching. So somewhere, beneath both of our languages, there must be a third one, a deeper grammar that contains them both. We have not heard it yet. We may not hear it in our lifetimes, but the search for it is one of the quietest and most patient adventures in all of science, carried out in chalk on blackboards, in long equations, in experiments so delicate they can almost listen to the hum of empty space. Over the next few hours, We will drift slowly through this open question. We will visit the smooth sheet and the restless foam. We will sit at the edge of black holes, and at the first instant of time, we will not solve the mystery. No one yet can. We will only wonder at it together, gently, the way one wonders at a sky full of stars whose names we do not know. Before we wander into the deep mystery, let's sit for a while with the first of our two languages, the one that speaks of vast things, the language of space-time. Space-time is a word that physicists use to describe something quietly strange. It says that space and time are not two separate ideas. They are woven together into a single fabric. That fabric stretches between every star and every grain of dust. It holds the planets in their slow orbits and the galaxies in their slow spirals. And according to the theory we use to describe it, this fabric is perfectly smooth. The theory is called general relativity. A patent clerk named Albert Einstein finished it more than 100 years ago. In the year 1915, it replaced an older picture of gravity, one in which space was a fixed, empty stage, and time ticked the same way for everyone. In the new picture, space could stretch, time could slow, and gravity was no longer a force pulling things together. It was the gentle bending of the fabric itself. Picture a soft rubber sheet pulled tight in the dark. Now imagine a heavy ball set down in the middle. The sheet sags around it, forming a smooth curved bowl. A marble rolled past the ball follows that curve, looping inward as if drawn by some invisible hand. There is no hand. There is only the shape of the sheet. That is gravity in the simplest picture we have. The sun makes a wide, gentle dip in the fabric of space-time, and the Earth rolls around the inside of that dip year after year, without ever knowing it is falling. The numbers behind this picture are quietly enormous. Light travels through this fabric at about 300,000 kilometers per second. That is fast enough to circle the entire Earth more than 7 times in a single tick of a clock. And yet light takes more than 8 minutes to cross the gap between the sun and us. The sunlight warming your window tonight left its star before you sat down. Space-time is that wide, even between close neighbors. Push outward, and the distances grow strange. Light from the next nearest star takes more than 4 years to reach us. Light from the heart of our galaxy takes around 26,000 years. From the nearest large galaxy, called Andromeda, light takes about 2.5 million years. When you look up at it on a clear autumn night, you are seeing a glow that left its home before our species had learned to make fire. Space-time is the calm sea those signals drift across, and general relativity says that sea has no ripples too small to imagine. It is smooth all the way down. Smooth, that word matters. In Einstein's equations, you can zoom in on any tiny patch of space and find a gentle, continuous curve. There are no gaps. There are no grains. You can keep magnifying forever, and the fabric stays as soft and unbroken as still water. Time in the same picture flows like a quiet river. It can run faster in some places and slower in others, depending on how strong gravity is. But it never skips, it never stutters, it never breaks into pieces. This smoothness is part of what makes the theory so beautiful, and part of what makes the theory so generous in its predictions. It tells us how planets orbit. It tells us how light bends around galaxies. It told us, long before we could see them, that black holes should exist, and that ripples in space-time, called gravitational waves, should travel outward from violent events. We have since heard those ripples in our instruments, faint and slow, washing in from collisions billions of years away. The smooth fabric works. It has been tested again and again, and it has not yet failed. And yet the mystery begins right here, in this gentle picture, because the other language we use to describe the universe, the one that governs the very small, says the world is not smooth at all. It says reality is grainy, restless, made of probabilities and jumps. The two pictures both work in their own places. Neither has been broken, but they describe the world as if they were describing two different worlds. For tonight, hold only the first picture in mind, the wide, dark sea, the slow curve around every star, a fabric so soft that you could in theory zoom in forever and find no edges. Whether that smoothness is truly real or only an illusion that hides something stranger underneath is a question we will sit with for many quiet hours to come. If the smooth curve of spacetime is one half of our puzzle, the other half began as a strange, persistent hum. In the early years of the 20th century, physicists were trying to understand the smallest things in the world. Atoms, light, the tiny grains that make up matter. What they found did not behave the way anyone expected. Particles flickered in and out of view. Light acted like a wave one moment and like a tiny bullet the next. Energy came in small, fixed packets, never in smooth flows. The world at the smallest scale seemed to be made of something restless, something that refused to sit still. This was the birth of quantum mechanics. It did not arrive all at once. It came slowly through a long chain of puzzling experiments. Heated metals glowed in patterns the old physics could not explain. Electrons jumped between levels inside atoms without crossing the space between. Light, striking certain metals, knocked loose tiny charged particles, but only if the light had a certain color, not a certain brightness. Each clue, taken alone, was small. Taken together, they pointed to a hidden layer of reality, a layer where the rules of everyday life simply did not apply. By the late 1920s, a strange new picture had taken shape. At the smallest scales, the world was not made of solid things sitting in fixed places. It was made of probabilities. A particle did not have a clear position until you looked. Until then, it was a kind of smeared cloud of possible locations. Two particles, once linked, could share a connection that crossed any distance faster than light could travel between them. None of this matched the calm, smooth world that Einstein had described, and yet every experiment agreed. The math worked. Predictions came true, over and over, to astonishing precision. In the decades that followed, a deeper version of quantum mechanics began to grow. Physicists started to wonder what was underneath the particles themselves. The answer, slowly built up through the middle of the 20th century, was the quantum field. The idea is gentle but strange. Imagine that the whole of space is filled everywhere with invisible fields. One field for electrons, one for photons, the particles of light, one for each kind of matter. These fields stretch across every empty room, every dark valley between the stars, every patch of vacuum between galaxies. They are always there, and they never stop trembling. A particle in this view is not a tiny ball. It is a small ripple in its field. An electron is a quiet vibration in the electron field. A photon is a small wave in the electromagnetic field. When the field is calm, the particle is at rest. When the field shakes harder, the particle carries more energy. The whole universe, by this picture, is woven from these soft humming layers. And even when nothing is happening, the fields are not silent. They flicker with tiny restless motions, called quantum fluctuations. Brief particles appear, then vanish again, faster than any clock can measure. This restless hum is not just a fancy idea. It has been tested in many quiet ways. Place two flat plates very close together in empty space, and they feel a small push toward each other. That push comes from the fluctuations of the field between them. Measure the magnetic strength of an electron with great care, and the answer matches the quantum field prediction to many decimal places. No theory in the history of science has been checked against nature as carefully as this one, and none has passed so many tests. And yet, gravity is missing from the picture. The quantum fields describe almost every force we know. The force that holds atoms together, the force that lights up the sun, the force that binds protons inside their tiny shells. Each one fits into the language of fields and ripples. Gravity does not. Gravity, in Einstein's picture, is the soft bend of space-time itself. There is no field on top of space. The space is the field. And no one has yet found a clean way to describe that bending in the same language as the trembling quantum world. So this is how the second half of our mystery was born, from heated metals and stubborn experiments and strange flashes of light, from a picture of the world as a quiet, humming cloth of fields, never still, never empty. A picture that works beautifully for almost everything, except the one thing that holds the stars and galaxies in their slow, sweeping shapes. Why the two pictures will not meet is the question we will sit with next. If you could somehow pull a small piece of the universe out and examine it on a table, what would you find inside it? At the level we live at, the answer feels easy. There is matter, made of atoms. There is light, made of photons. There is space, which seems to be the empty room everything else sits in. And there is time, which seems to be the quiet drumbeat that lets things change. 4 ingredients, a simple recipe. The deeper you look, the more that simple recipe falls apart. Atoms turn out to be mostly empty, with tiny dense nuclei surrounded by fuzzy clouds of electrons. The nuclei themselves are made of smaller things called quarks, held together by forces we describe with quantum fields. And those fields, when you study them closely, are not really things at all. They are patterns of probability humming through what we used to call empty space. Now ask the same question about space-time itself. What is it made of? Here, the equations of general relativity give a very different answer. Space-time is not built from smaller pieces. It is smooth. It is continuous. You can divide it as finely as you like and never reach a smallest part. In Einstein's picture, space-time is more like a calm sheet of dark silk than a pile of grains. This is where the two languages of physics begin to whisper past each other. Quantum mechanics describes a universe that is grainy at the bottom. Energy comes in little bundles. Particles appear and vanish. Even the vacuum is full of tiny flickers. General relativity describes a universe that is smooth at the bottom. Space bends gently. Time flows without jumps. One theory says the deepest layer is restless and chunky. The other says the deepest layer is calm and unbroken. For most of what we see, this disagreement does not matter. Stars and planets are huge, so we use gravity. Atoms and particles are tiny, so we use quantum rules. The two theories live in different rooms and rarely meet, but the universe does not have separate rooms. Everything is made of the same stuff, woven into the same fabric, and the elements that fill your body and your sky are proof of how tangled those layers really are. Consider the iron in your blood. Every atom of it was forged inside a star that lived and died long before our sun was born. Deep in that star's core, gravity squeezed lighter elements together until they fused into iron. Gravity, the smooth bending of space-time, made the pressure. Quantum forces, grainy and probabilistic, made the fusion happen. Neither theory alone can tell the whole story of one iron atom. The same is true of the water in the ocean. Some of it may have arrived on icy comets, drifting in from the cold outer reaches of the early solar system. The hydrogen in those water molecules formed in the first few minutes after the universe began, when conditions were so extreme that gravity and quantum behavior were tangled together in ways we still cannot fully describe. The oxygen came later, cooked inside stars. Every sip of water is a small archive of unsolved physics. Even the carbon in your skin sits at this crossroads. It was built inside ancient stars through a delicate quantum dance, then scattered across the galaxy when those stars exploded. The explosion itself was governed by gravity collapsing a stellar core to densities where our two theories should both apply at once. And at that moment, in those final fractions of a second, the equations we trust most begin to disagree with each other in ways no one has yet untangled. So when we ask what the universe is made of, we are really asking two questions at once. What are the ingredients? And what is the bowl that holds them? The ingredients seem to be quantum. The bowl seems to be classical. The recipe demands both, and yet the cookbook only has half the pages. Some researchers suspect the bowl is also quantum, and we simply have not learned to see its grains. Others suspect the ingredients are also smooth, at a level deeper than we have measured. A few wonder whether the bowl and the ingredients are not separate at all, and the divide, we feel, is only a mistake of our own imagination. None of these ideas has won tonight. As you lie here, the iron in your blood and the water on your tongue carry traces of that unfinished question. They were made in places where our equations refuse to meet, and we still do not know what language those places truly speak. Far out in the deep dark, in places where stars once burned bright, something strange has happened. The star ran out of fuel. Its outer layers blew away into space, and the heavy core that remained began to fall inward, pulled by its own weight. Nothing inside that core was strong enough to hold it up. Not the pressure of hot gas, not the push of particles against each other. Gravity simply won, and kept winning, and pulled the matter into a space smaller than a city, then smaller than a house, then smaller than a thought. This is the place where our two great theories begin to argue with each other. A black hole is a region where gravity has grown so strong that not even light can climb back out. Around it lies the event horizon, the invisible boundary past which nothing returns. Inside that boundary, gravity keeps pulling, mass keeps falling, and according to general relativity, the matter does not stop. It collapses into a single point of zero size and infinite density. That point is called a singularity. The word sounds clean, but it is really a confession. A singularity is what the equations spit out when they no longer know what to say. Density becomes infinite. Curvature becomes infinite. The smooth fabric of space-time, which had behaved so beautifully across galaxies and stars, suddenly tears itself apart in the middle of its own mass. General relativity, the theory that maps the largest things in the universe, breaks down at the very heart of the object it predicted. This is where quantum mechanics should step in. At such tiny sizes, quantum rules must apply. Particles cannot truly sit at a single point. They blur, they jitter, they behave like waves of possibility rather than little marbles. So the matter falling into a black hole should never quite collapse to nothing. Something should stop it. Some pressure, some quantum fuzziness, some new behavior of the very small. But when physicists try to write down what that something is, The equations refuse to cooperate. Gravity and quantum mechanics, asked to share a single room, begin shouting in different languages inside that small region. Every force we know is pushed to its limit. Tidal forces, the stretching pull of gravity that grows stronger the closer you get, becomes so fierce they could pull a single atom into a thread. The temperature of matter, spiraling toward the horizon, climbs into the millions of degrees. Magnetic fields, twisted by the spin of the dying core, wind themselves into vast invisible ropes that fling jets of plasma across thousands of light years. And yet, all of this furious activity happens around the edges. The true puzzle waits deeper in, where no signal escapes and no instrument can reach. One idea is that the singularity is not real. Some researchers wonder if a fuller theory of quantum gravity will smooth that infinite point into something finite. The matter might compress to a tiny but ordinary lump, held up by a kind of quantum pressure we do not yet understand. Loop quantum gravity, one of the candidate theories, hints that space itself comes in tiny, indivisible pieces, and that those pieces refuse to be crushed past a certain limit. In that picture, the collapse halts, the star bounces. A new region of space-time might even open on the other side. A competing idea comes from string theory. In this view, the smallest objects in the universe are not points, but tiny vibrating filaments. If matter is made of strings rather than dots, then perhaps nothing ever shrinks to zero size in the first place. The singularity dissolves into a tangle of vibrations. Some versions of the theory suggest that what looks like a singularity from outside is really a thick, fuzzy ball of strings filling the inside of the black hole. Others suggest the interior is stranger still and may not exist in the way we imagine. None of these pictures has been confirmed. The center of a black hole is sealed away by the horizon, hidden from every telescope we have built or could build. We cannot send a probe. We cannot bounce a signal. We can only listen for ripples in space-time from collisions far away and study the soft glow of matter swirling at the edge. The deep interior remains a closed letter, addressed to physics, still unopened. So, the trouble at the center is not just a trouble of math. It is the place where our understanding of force, of pressure, of gravity, of matter itself runs out of road. Something is happening in there. We simply do not yet have the words for it. To feel the size of the puzzle, picture the very first instant of the universe. Not the first second, not the first millisecond, the first sliver of time so brief that ordinary words begin to lose their meaning. Physicists give this sliver a name. They call it the Planck time, S. It lasts about 10 to the negative 43 seconds. That is a decimal point, followed by 42 zeros, and then a 1. If you tried to count those zeros at 1 per second, you would still be counting long after our sun had burned out. In that first flicker, the entire observable universe was smaller than a single atom, smaller than a proton, smaller than anything we have ever seen or touched. All the stars that would one day form, all the galaxies, all the dust and ice and warm planets, all of it was packed into a space so tiny that you could not even call it a space in the normal sense. The fabric of reality, if it was a fabric at all, had not yet stretched out into the calm geometry we know today. To make this feel real, try a small comparison. Imagine shrinking the entire Earth down to the size of a single grain of sand. Now imagine shrinking that grain of sand down again by the same amount, and again, and again. You would still not be close to the Planck length. That length is about 10 to the negative 35 meters. It is the smallest distance that has any clear meaning in physics. Below it, the very ideas of here and there begin to soften. Like ink running on wet paper. Temperature in that first moment was beyond anything our instruments could ever recreate. Some estimates place it near 10 to the 30 degrees. Not thousands, not millions. A 1 followed by 32 zeros. The hottest part of the sun's core, by comparison, sits around 15 million degrees. That is a warm bath next to what the early universe held. Every kind of particle we know, and likely many we do not, swam together in a single roaring soup. Forces that now feel separate were braided into one. This is the place where the missing bridge matters most. General relativity, the smooth and graceful theory of curved space-time, was designed for things that are large and slow. Quantum mechanics, the strange and grainy theory of the very small, was designed for things tiny and quick. In the first instant of the universe, the cosmos was both at once. It was as small as the smallest quantum thing and as dense as the strongest gravitational thing. Both rule books had to apply. Both rule books broke. When physicists try to use the equations of general relativity at the Planck scale, the math returns infinities. Curves become endlessly sharp, densities become endlessly large. When they try to use quantum mechanics at that same scale, the gentle ripples of probability turn into a storm so wild that the equations stop making predictions at all. It is as if you asked two trusted maps for directions, and both pointed off the edge of the page. So the first moments of the universe are not really a story we can tell with confidence. They are a quiet war. We can describe what came soon after, when the cosmos had grown to the size of a grapefruit and cooled enough for known physics to take hold. But the first sliver, that thinnest slice before any clock we own can tick, remains a mystery shaped like a question mark. Some researchers wonder if time itself did not exist there. They picture a kind of timeless fog, a state where before and after had no meaning yet, and from which time slowly crystallized as the universe cooled. Others suspect that what we call the beginning was not really a beginning at all, but a bounce from an earlier universe that collapsed and then expanded again. A few suggest that space and time emerged together from something more basic, something we have not yet learned to name. None of these ideas has won. Each rests on hopeful math and quiet patience. The first moments of the universe sit there in the dark, holding the answer to why our two great theories will not speak the same language, refusing to whisper it back to us. It is a strange comfort, lying in a calm room, to know that the smallest, hottest, briefest piece of everything that ever was is still waiting to be understood. The numbers do not need to be memorized. They only need to be felt. A universe smaller than an atom, a second too short to count, a heat beyond imagining, and inside it, a secret still kept. If you could shrink yourself down past the scale of atoms, past the scale of quarks, past every level we have ever measured, you might begin to glimpse the surface of the universe as some theories imagine it. This surface is not a place exactly. It is the texture of reality at its smallest grain. And because no experiment has ever resolved it, what you see depends entirely on which quiet guess you choose to believe. Picture, for a moment, the world as string theory paints it. The points we once called particles are no longer points at all. They are tiny filaments, like threads of soft light, each one no thicker than a whisper. These threads vibrate. Each note they play becomes a different particle. A low hum might be an electron. A higher pitch might be a quark. The whole zoo of matter in this picture is just one kind of string, singing in many different keys. If you could hover above this hidden layer, you might see a shimmering field of luminous filaments, looping, twisting, opening and closing, like the strings of a vast and silent instrument. It is a beautiful picture. It is also, so far, untested. No experiment has ever seen a string. The threads, if they exist, are so small that the energies needed to glimpse them lie far beyond anything our machines can reach. String theory remains a careful mathematical idea, elegant on paper, quiet in the lab. Some researchers find its beauty persuasive. Others wonder whether beauty alone is enough. Now let the picture shift. Set the strings aside and imagine instead the surface that loop quantum gravity proposes. Here, space itself is not smooth, it is woven. If you could look closely enough, you would see tiny loops, each one a small unit of space, linked together into a kind of fabric. The threads are not particles, they are the very stitches of the void. Volume, in this picture, comes in discrete pieces. Area comes in discrete pieces. The smooth sheet of space-time we learned about earlier turns out to be, at this level, something like a chainmail of light. Step back far enough, and the weave blurs into a single soft surface. Step close enough, and the loops reveal themselves, finite and countable. Loop quantum gravity offers something string theory does not. It tries to keep gravity at the center of the story. Space is not a stage on which strings perform. Space is the thing being built. But this picture, too, faces hard questions. It has not yet shown clearly how the familiar particles of matter emerge from its loops. It has not yet been tested by any experiment we can perform. Like string theory, it waits. There are quieter guesses still. Some researchers explore what they call causal dynamical triangulations. In this picture, space-time is built from tiny four-sided pieces, glued together according to careful rules about cause and effect. Imagine a vast mosaic of glassy tetrahedra, each one a small chip of reality, fitting together to form the smooth curves we see at larger scales. Others explore the idea of causal sets, in which the universe is a sparse scattering of events, like a fine sprinkle of dust, with each grain connected to others only by the thread of before and after. Each of these pictures gives the surface of reality a different texture. Strings give it music, loops give it weaving, triangulations give it mosaic, causal sets give it a kind of luminous mist, and none of them has yet been confirmed, none has yet been ruled out. They sit beside each other, like quiet sketches in a notebook, each one waiting for evidence that may or may not arrive. What is striking is that they all agree on one thing: the smooth, continuous space-time of general relativity cannot be the final word. Something more fine-grained must lie beneath it. The disagreement is only about the shape of that grain. Some imagine it musical, some imagine it knotted, some imagine it scattered. The universe itself has not yet told us which sketch, if any, is the true one. So when you imagine standing on this hidden surface, you must hold several pictures at once. A field of glowing threads, vibrating softly. A weave of tiny loops, packed tight as honeycomb. A mosaic of glassy shapes, fitted edge to edge. A drift of cause and effect dust, suspended in the dark. Each one is a guess made with great care by people who have spent their lives staring into the math. And the deepest mystery is that the universe at this level may look like none of these. It may look like something we have not yet thought to imagine. To go deeper into this mystery, we have to shrink. Shrink past atoms, past the tiny humming parts inside them, past the quarks that make up those parts. Keep shrinking, keep going, until the ruler in your mind runs out of marks. Somewhere down there, at a scale so small, the imagination begins to slip. You reach a quiet wall. Physicists call it the Planck scale, and no one has ever seen what lies on the other side. The Planck length is roughly 10 to the minus 35 meters. That number is not a friendly one. It means a length so small that if you blew up a single atom to the size of the entire observable universe, the Planck length inside that atom would still be smaller than a grain of sand. It is the place where the rulers of physics seem to dissolve. Both general relativity and quantum mechanics agree that something strange must happen here. Neither one can tell us what. This is the depth where the missing bridge would have to live. At larger scales, gravity is gentle and smooth. Space-time curves like soft silk under the weight of stars. At the Planck scale, that smoothness may not survive. Quantum mechanics says that at very small sizes, every quantity flickers. Energy borrows from the void and pays it back. Fields tremble in place. If gravity behaves the same way, then space-time itself should tremble too. The smooth silk would become something else, something restless, something that the equations of general relativity were never built to describe. One picture, sketched long ago by the physicist John Wheeler, calls this the quantum foam. In this idea, space-time at the Planck scale is not a calm sheet, but a churning sea of tiny bubbles. Distances stretch and shrink. Loops of space open and close. The very ideas of here and there lose their crisp edges. It is a beautiful picture, but it is only a picture. No experiment has ever confirmed the foam, and other theorists doubt it looks anything like that at all. Some suspect the structure is more orderly, woven from neat, discrete units. Some suspect the smoothness simply continues, all the way down, and the foam is a mirage of our incomplete math. The Planck scale also gives us the Planck time. This is the time it would take light to cross one Planck length. It comes out to about 10 to the minus 43 seconds. Below that, the word before may have no meaning. The word after may have no meaning. Time itself, like space, may stop being a steady current and become something grainy, something that ticks in tiny indivisible beats. Or it may not. The honest answer is that no one knows. We have only the suggestion that something must change, because both theories begin to give nonsense answers when pushed past this wall. What makes the Planck scale so silent is that we cannot reach it. To probe such small distances, a particle accelerator would need to be unimaginably powerful. Some estimates suggest it would have to be larger than a galaxy. The energies involved are so high that any experiment trying to look directly at the Planck length would, by the rules of general relativity, collapse into a tiny black hole before any measurement could be made. The act of looking destroys the thing you are looking at. Nature seems to have built a privacy wall around its deepest secrets. So researchers look sideways. They search for faint echoes of Planck scale physics in the light from distant gamma-ray bursts, hoping that quantum foam might slow some colors of light by an unimaginably small amount over billions of years of travel. The searchers have, so far, found nothing unusual. That absence is itself a clue. It tells us that whatever is happening at the Planck scale, it is gentler, or quieter, or stranger than the simplest pictures predicted. The wall stays silent, and yet we know something must be there. The math of general relativity, pushed past the Planck scale, breaks. Lengths become negative. Probabilities climb above one. Infinities pile on infinities. These are the symptoms of a theory speaking outside its native tongue. The same happens to quantum field theory. When gravity is forced into its equations, both languages stutter. Both fall silent at the same wall. What lies past it may be a deeper smoothness, or a finer grain, or a structure we have no words for yet. The bridge between space-time and quantum mechanics, if it exists, must be built down there in that quiet dark. For now, We stand at the edge, listening, and the wall gives nothing back. There is a strange and quiet question hiding inside the word gravity. We grow up thinking of it as a force, like a hand that pulls apples toward the ground and moons toward their planets. But the deeper physics looks, the less it behaves like the other forces of nature. And one of the oldest puzzles in the search for a unified theory begins right there, with a simple wondering about what gravity actually is. The other forces have a rhythm we can almost hear. Electricity and magnetism pulse through fields carried by tiny packets of light. The strong and weak forces inside atoms work through small messenger particles, exchanged in fast repeating patterns. Each one has a clear quantum heartbeat. Each one fits neatly into the language of quantum mechanics, with its discrete steps and its probabilities. They are forces in the truest sense, made of countable interactions. Gravity does not seem to play that game. In Einstein's picture, gravity is not a force at all. It is the shape of space-time itself. A planet does not pull on a moon by reaching out across the void. Instead, the planet bends the smooth fabric around it, and the moon simply follows the gentlest path through that curve. What we feel as weight is the geometry of space, gently guiding us downward. The cycles of orbit, the long arc of a comet, the slow fall of a leaf, all of them in this view are just objects coasting through a quietly curved landscape of space and time. So one possibility is that gravity only looks like a force from the outside, underneath. It may be something more like a backdrop, a stage that bends in response to whatever stands upon it. In this picture, asking for a quantum theory of gravity might be asking the wrong question. You cannot easily quantize a stage. You can only quantize the actors moving across it. But another possibility pulls in the opposite direction. Many researchers wonder whether gravity, despite appearances, must still have a quantum side if every other part of nature pulses in discrete steps. It seems strange for gravity alone to remain perfectly smooth. The hypothetical particle that would carry gravity is called the graviton, a kind of soft messenger riding along the curves of space-time. No experiment has ever detected one. The pull of gravity is so faint compared to the other forces that a single graviton may be forever beyond the reach of any instrument we can imagine building. Between these two views lies a quiet tension that has lasted for nearly a century. Is gravity a force in disguise, waiting to be tamed into quantum form? Or is it something else entirely, more like the breathing of space itself, and the rest of physics will eventually have to bend to match it? The rhythms here are slow. Generations of physicists have circled this question, each adding a small turn to the wheel. There is yet another idea worth sitting with. Some researchers suggest that gravity is not fundamental at all. In this view, it might be what they call an emergent phenomenon, the way temperature emerges from the jostling of countless atoms. No single atom has a temperature, yet together, in motion, they create one. Gravity, by analogy, might arise from deeper quantum patterns we have not yet learned to see. The cycles of planets and the bending of light would then be the large, slow echoes of something tiny and statistical far below. If that is true, then space-time itself would be a kind of average, smooth on the outside, grainy and busy on the inside. The orbit of a moon would be the soft summary of unimaginably many small quantum events, the way a calm ocean surface hides the chaotic motion of every drop beneath. This idea is beautiful, but it remains a guess. No one has shown, in full mathematical detail, how the curves of Einstein's universe could rise out of quantum behavior in just the right way. And so the cycles of this question keep turning. Each decade brings new approaches, each one a careful step into the same fog. Some treat gravity as a force to be quantized. Some treat it as geometry to be respected. Some treat it as an illusion of something deeper. None of them, yet, has crossed the bridge. What remains open is whether gravity belongs in the same family as the other forces, or whether it is something quieter, older, more structural, the silent shape inside which all the other forces sing. The honest answer, tonight, is that we still do not know. We only know that the question keeps returning, gently, like the tide, washing over the same shore in slightly different light each time. Of all the ideas that sit beside this great unsolved puzzle, none is stranger than the quiet question of time itself. We live inside time. We feel it move. We watch it flow through every moment of our lives, steady and gentle, like a slow river. And yet, when physicists try to fit time into the equations of quantum gravity, something very odd happens. Time begins to fade. It loses its grip. In some formulations, it disappears from the math entirely. This is one of the deepest neighbors of our central mystery. The clash between general relativity and quantum mechanics is not only about space, or particles, or forces. It is also about the soft, steady tick of time. And the two theories do not agree on what time is. In general relativity, time is woven into the fabric of space-time. It bends near heavy objects. It stretches when you move quickly. A clock on a mountain ticks a tiny bit faster than a clock in a valley below. Time in this picture is part of the landscape itself, shaped by gravity and by motion. There is no single universal clock for everyone. Each observer carries their own. In quantum mechanics, time plays a very different role. It is not part of the system being studied. It sits outside, like a background rhythm, a steady beat that the equations rely on, but never explain. Quantum mechanics tells you how a particle changes from one moment to the next, but it treats those moments as given. Time is the stage. The quantum world dances upon it. When physicists try to join the two ideas, the stage and the dancer collide. If time bends and stretches like space, how can it also be a steady background beat? If gravity warps the very clocks we use, how do we measure quantum events at the smallest scales? At some point, the question becomes almost impossible to ask, because the tools for asking it begin to dissolve. One famous attempt to write down a quantum theory of gravity produced an equation in which time simply does not appear. The universe, in this formulation, seems frozen. Nothing flows, nothing moves, and yet we know, from our own lives, that time clearly does move. Something is missing. The math is incomplete, or our understanding of what time really is needs to be rebuilt from the ground up. Some researchers wonder if time is not fundamental at all. Maybe time is something that emerges from deeper, timeless relationships between parts of the universe. A bit like temperature, which only makes sense when many particles move together. A single particle has no temperature. Perhaps a single piece of the universe has no time, and only the whole, taken together, gives rise to the gentle current we feel. Others push back on this view. They argue that time is far too central to physics to be merely an illusion or an emergent shadow. They suggest that time is real, fundamental, and that our theories simply have not caught up with it yet. In this view, the answer will not be to remove time from the equations, but to find a new way to keep it in. A third group wonders if time might be discrete at the smallest scales, not a smooth river, but a series of tiny separate moments, like the frames of a slow film. Loop quantum gravity, for instance, hints at the possibility that time itself might come in small steps, each one smaller than any clock could ever measure. Other approaches imagine time as still continuous, but woven differently into the deeper structure of reality. No experiment has yet shown which of these pictures is correct. The smallest time we can currently measure is still enormously larger than the scales where these questions live. And so the debate continues, quietly in equations and conversations, with no clear winner. What makes this puzzle so strange is how close it sits to our daily experience. Time is the most familiar thing in the world. We trust it, we plan by it, we feel it in our breath and our heartbeat. And yet, when we look closely, when we ask the universe what time really is, the answer slips through our fingers. The neighbor of space-time is not only space, it is also the soft, steady passage of moments. And both halves of that pairing, space and time, become uncertain when we press them into the smallest realms. The mystery of how to unite gravity and quantum mechanics is also, in a quiet way, the mystery of what a moment is. We do not yet know, and tonight, that is a calm and lovely thing to wonder about, as one moment slowly gives way to the next. Picture, for a moment, the emptiest place you can imagine, a patch of space between galaxies, where no star shines, no planet drifts, no breath of gas stirs. You might expect such a place to be truly empty, a perfect nothing, a clean slate of pure dark. The strange thing is, no such place exists. Even in the deepest void, the vacuum is not still. According to quantum mechanics, empty space is alive with a soft, restless flicker. Particles wink into being and vanish again too quickly to catch. Tiny pairs of matter and antimatter rise from nothing, touch and dissolve back into the dark. The vacuum hums, it trembles, it refuses to be empty. This shimmering activity has a name. Physicists call it the zero-point field, the lowest possible state of energy in space. And yet, that lowest state is not zero. It is a quiet, ceaseless boil. The evidence for this hidden boil is real and measurable. In 1948, a Dutch physicist predicted that if you placed two flat metal plates very close together in a vacuum, the restless flicker between them would be slightly weaker than the flicker outside. The plates would feel a tiny push toward each other, driven by the difference. Decades later, experiments confirmed this gentle pressure. The vacuum was indeed pressing on the world. So far, so good. Quantum theory describes the humming vacuum with stunning precision. The trouble begins when we ask a simple question. How much energy does this restless vacuum actually hold? And what does that energy do to space-time itself? Here, the two great theories crash into each other once more. General relativity tells us that energy bends space. Any energy, anywhere, should curve the fabric around it. So the energy of the vacuum, spread through every cubic inch of the universe, should warp the cosmos in a measurable way. It should push the universe outward or pull it inward depending on its sign and strength. We can measure the actual push. The universe is expanding, and that expansion is gently speeding up, driven by something we call dark energy. Whatever dark energy is, its value is very small, a tiny positive pressure, just enough to nudge galaxies apart over billions of years. Now comes the strange part. When physicists try to calculate the energy of the quantum vacuum and compare it to the energy that actually pushes the cosmos apart, the two numbers do not match. They do not even come close. The predicted value, depending on how you calculate it, is larger than the observed value by a factor, with as many as 120 zeros after it. 120 zeros. This is sometimes called the worst prediction in the history of physics. Two theories, each magnificent in its own home, give an answer for the same quantity, and they disagree by an amount almost too large to name. Something clearly is missing. One possibility is that the calculation of the vacuum energy is being done wrong, and some deeper rule cancels nearly all of it out. Some researchers wonder whether a hidden symmetry, not yet discovered, sweeps the huge number down to almost nothing, while leaving the tiny remainder we observe. Others suggest that what we call dark energy is not vacuum energy at all, but something else entirely, a slowly changing field that only mimics a constant. A different view goes further. Perhaps general relativity itself stops working at the largest scales, just as it stops working at the smallest. Perhaps the smooth curve of space-time is only an approximation, and a fuller theory would explain why the vacuum energy and the cosmic expansion do not match in the way we expect. There are even quieter ideas. Some thinkers propose that we live in one universe among many, and that the gentle value of dark energy in our cosmos is simply the one that allows galaxies, stars, and observers to form. In other regions, a vacuum might press harder or pull more strongly, with no one there to wonder about it. None of these ideas has been confirmed. The mismatch between the quantum vacuum and the gravitational vacuum sits like a stone in the path of every attempt to unite the two theories. It is the loudest hint that something fundamental is still hidden from us. For now, the vacuum keeps its secret. It hums beneath every star and every empty stretch of sky. It nudges metal plates together in laboratories. It drives galaxies apart across billions of light years, and somewhere inside its restless flicker is a number we cannot yet calculate, holding the door closed on a deeper picture of reality. The emptiness is not empty, and we still do not understand what fills it. There is a quiet detail about black holes that most people never hear, and it sits at the heart of our tonight's mystery. It has to do with information, not the kind written in books, but the deeper kind, the kind that describes exactly what a particle is doing, where it is, and how it is connected to everything else. In quantum mechanics, this information is sacred. It cannot be created. It cannot be erased. It can only shift and rearrange, like cards in an endless game that never loses a single card. This rule has a soft name. Physicists call it unitarity. It simply means that if you knew everything about a system right now, you could, in principle, run the math backward and recover its past. Nothing is ever truly lost. The universe, in the quantum view, has a perfect memory. And then there is the event horizon. The event horizon is the gentle, invisible edge around a black hole. It is not a wall. It is not a surface you could touch. It is simply the place past which the pull of gravity becomes so strong that nothing, not even light, can climb back out. From the outside, it looks like a smooth, dark sphere, quieter than anything else in the sky. From the inside, no signal can ever return. Now picture a single particle drifting toward that edge. It carries information with it. Maybe it carries the memory of the star it once belonged to. Maybe it carries the faint quantum imprint of every interaction it has ever had as it crosses the horizon. From the outside view, it seems to fade and stretch and slow until it becomes a whisper too faint to read. According to general relativity, that information is simply gone. It has fallen into a place from which nothing returns. The black hole eats it, holds it, and eventually, over unimaginable spans of time, evaporates away through a slow drizzle of radiation. When the black hole is gone, the information seems gone with it. According to quantum mechanics, this cannot happen. The cards cannot vanish. The memory must survive somewhere. This quiet contradiction has a name. Physicists call it the black hole information paradox, and it is one of the softest, most beautiful symptoms of the missing bridge we have been wondering about. Two theories, both extraordinarily successful, give two different answers about the same patient particle. One says the information is erased. The other says it is impossible to erase. The puzzle deepens when you look closely at the radiation a black hole gives off. This faint glow is so cold, so dim, that no telescope has ever seen it from a real black hole. It is predicted by theory alone. The radiation appears to be almost perfectly random. It looks like static. It looks like noise. If it truly carries no information about what fell in, then quantum mechanics has been quietly broken at the edge of every black hole in the universe. Some researchers wonder if the information is hidden inside the radiation in subtle correlations we have not yet learned to read. Like a long letter written in invisible ink, the message could be there, just waiting for the right light. Others wonder if the information is smeared across the event horizon itself, stored in a thin, shimmering layer that records every detail of what crossed. In this picture, the horizon has a memory of its own, and the black hole is less a hole and more a vast, quiet library. A different idea suggests that information might never actually fall in at all. From the outside, infalling matter seems to slow and freeze near the horizon, never quite crossing. Perhaps, in some sense, the universe keeps a copy on the outer surface, even as the original passes through. Two versions of the same particle, in two different descriptions, neither of them wrong. None of these ideas is settled. Each one bends some other rule we hold dear. Each one solves part of the puzzle and leaves another part open. The question of where information goes when it crosses a horizon is, in many ways, the same question as where gravity meets the quantum world. The two mysteries are one mystery. Wearing two different costumes, there is something gentle about sitting with this. A black hole is silent. It does not announce its paradoxes. It simply hangs in space, calm and dark, while inside its math, two of our greatest theories whisper opposite answers to each other. The event horizon may be the quietest contradiction in the universe. A perfectly smooth surface, hiding a question we cannot yet answer, holding memories we do not yet know how to read, and somewhere in that soft contradiction, the bridge we are looking for may already be waiting. The story of the holographic idea begins not with a grand telescope or a sweeping cosmic survey, but with a quiet puzzle about the surface of a black hole. In the early 1970s, a young physicist named Jacob Bekenstein was thinking about something that should have been simple. He wanted to know what happened to information when an object fell past the edge of a black hole. The laws of thermodynamics, which had served physics so well for a century, seemed to demand that nothing in the universe could ever lose its record of disorder. Yet a black hole, by every account, seemed to swallow that record whole. Bekenstein made a strange suggestion. He proposed that a black hole carried entropy, a measure of hidden information, and that this entropy was tied not to its volume, but to the area of its outer surface. The idea was met with skepticism at first. Even Stephen Hawking, who would soon become one of the most important voices in the field, initially doubted it. But Hawking's own calculations, done a few years later, confirmed the strange truth. Black holes did radiate, they did carry temperature, and their entropy did scale with the area of the horizon, not with the volume of space. Inside, this was the first quiet hint of something deeply odd about the universe. In every other system we knew, the amount of information you could store grew with the volume of the container. A larger box could hold more. But for black holes, the rule was different. Everything you could ever know about what fell in seemed to be written, in some mysterious way, on the two-dimensional skin of the horizon itself. The interior, vast and dark, contained no extra room for secrets. 2 decades later, in the 1990s, the physicists Gerard Hooft and Leonard Susskind took this strange clue and pushed it as far as it would go. They asked a startling question. What if this rule was not just true for black holes, but true for every region of space? What if the entire three-dimensional world we move through is, in some deeper sense, encoded on a two-dimensional surface far away? They called this proposal the holographic principle. The name came from the optical holograms that store a three-dimensional image on a flat sheet of film, where every patch of the sheet contains, in subtle interference patterns, the whole picture. The idea sounded almost like poetry, but in 1997, a young physicist named Juan Maldacena gave it mathematical bones. He found a precise example in which a certain kind of curved space-time, full of gravity, behaved exactly like a quantum field theory, living on its lower dimensional boundary. The two descriptions, though they looked nothing alike, gave the same answers to every question. Gravity in the interior was in some sense equivalent to a gravity-free quantum dance on the edge. Physicists call this relationship a duality. It remains one of the most studied results in the entire search for quantum gravity. What Maldacena's work suggested was both beautiful and unsettling. Perhaps space-time, the smooth fabric Einstein described, is not the deepest layer of reality. Perhaps it emerges like a projected image from quantum information arranged on a distant boundary. If true, this would offer one of the cleanest bridges yet between the two great theories. Quantum mechanics would live on the edge, gravity would live in the projection. The contradiction between them would dissolve, because they would simply be two ways of describing the same thing. And yet the picture is far from complete. Maldacena's exact example uses a kind of space-time that does not match the universe we actually live in. Our cosmos appears to be expanding outward, while his model assumes a different shape entirely. Many researchers believe the holographic idea still holds in our universe, but no one has yet written down the precise version that would prove it. Other physicists wonder whether the holographic relationship is a deep truth about reality or a useful mathematical trick that happens to work in special cases. There are quieter critics too. Some suggest that the success of holography in certain models has pulled attention away from other promising paths. Loop, quantum gravity, causal set theory, and other approaches do not naturally fit the holographic frame. They ask whether the boundary description is fundamental at all, or whether it is one shadow among many cast by something we have not yet learned to see. So the holographic idea sits in a curious place. It is the closest thing modern physics has to a working bridge between the two great theories, and yet it remains, in many ways, a beautiful map of a country no one has fully visited. Picture, if you will, a perfectly calm lake on a windless morning. The surface looks like polished glass. You could mistake it for a single smooth sheet. But lean closer, kneel by the shore, and the illusion begins to fade. There are ripples, there are tiny droplets, small currents, little eddies. The smoothness was only a trick of distance. Some thinkers wonder whether space itself behaves this way. From far enough back, space looks calm, flat, and seamless. The light from distant stars travels through it without a stutter. Planets curve along their paths without any sign of bumps or seams. Yet, down at the smallest scales, far smaller than an atom, far smaller than the parts inside an atom, space might not be calm at all. It might be churning, it might be frothing. It might be made of something that is not space in any familiar sense. The physicist John Wheeler gave this idea a soft and memorable name. He called it Spacetime foam. The picture is strange. At the Planck scale, the smallest meaningful size we can speak of, space and time may bubble with tiny fleeting structures. Loops appear and vanish. Little pockets pinch open and close. The very shape of space may flicker. Whether this foam is real or just a useful mental image remains an open question. No instrument has ever seen it. We may never see it directly, but the idea sits at the heart of many guesses about how gravity and quantum mechanics might finally meet. Loop quantum gravity offers a different surprise. In that picture, space is not foam but fabric. The fabric is woven from tiny loops, and each loop carries a fixed unit of area or volume. Space in this view is grainy. You cannot cut it smaller than a certain size, just as you cannot cut a single grain of sand into half a grain and still have sand. If this is correct, then the smooth curves of general relativity are an illusion at large scale. The smoothness emerges from countless tiny grains, the way a beach looks smooth from a hilltop and rough underfoot. Other researchers find this hard to accept. They argue that no experiment has yet shown space to be grainy, and the math, while elegant, has not made predictions we can test. The question stays open. There is something stranger still. In quantum field theory, the vacuum is not empty. Even in a region of perfect dark, far from any star, the fields that fill the universe quiver. Pairs of particles flicker in and out of being, lasting only a moment before they cancel each other and disappear. These are called virtual particles, and their faint pressure has been measured in tabletop experiments. Two metal plates held very close together feel a tiny pull toward one another, because fewer virtual particles fit in the gap than outside it. The void is doing something. The void is restless, and nobody is entirely sure what the void truly is. This raises a quiet puzzle. If empty space carries energy from all this quantum trembling, then gravity should respond to it. Yet, when physicists try to calculate how much energy the vacuum should hold, they get a number wildly larger than what the universe actually shows. The mismatch is enormous, off by many, many orders of magnitude. Something is wrong with our picture, or something is missing, and no, one has found the missing piece. It is one of the clearest signs that the bridge between the two theories has not been built. There are other surprises in this strange territory. Some researchers wonder whether the speed of light itself might vary by the tiniest amount, when light of different colors travels across billions of years through foamy space. Telescopes have looked. So far, the light arrives together, color by color, with no detectable lag. This does not rule out space-time foam. It only tells us that, if the foam exists, it is gentler than some guesses predicted. Other models suggest the foam might be so subtle that no light, no signal, no instrument we can yet build could feel it. What lingers, as you settle into these thoughts, is the strange possibility that the smoothness of the world is borrowed from scale, borrowed from distance, borrowed from the fact that we are large and slow, and the universe down there is small and fast. The calm surface of the lake, the grain in the wood, the hush of an empty room, none of them may be as solid as they appear, and the texture of the void, whatever it truly is, waits patiently for someone to finally describe it in a language both theories can share. There is a quiet thread that runs through modern physics, and it has begun to look like one of the deepest clues we have. The thread is called Entanglement. It is a strange link between two quantum particles, a link so subtle that it has no clear place in our everyday picture of the world. Two particles can share a single quantum state even when they sit far apart. Measure one, and the other seems to know. Not through any signal we can trace, not through any wire or wave. They simply share a description, but neither one owns alone. For a long time, entanglement was treated as a curiosity, a puzzle for philosophers, and a tool for engineers building quiet new computers. But in recent years, some researchers have begun to wonder if entanglement might be more than a feature of small things. They wonder if it might be the very stitching that holds space together. If that guess is right, then the smooth fabric we walk through every day is woven from countless tiny quantum threads, all linked, all sharing information in ways we are only beginning to map. The idea goes by a gentle name. Some call it entanglement equals geometry. The thought is that two regions of space are close to each other because the quantum systems inside them are deeply entangled. Pull that entanglement apart, and the distance between them grows. Strip it away entirely and the connection dissolves, leaving two pieces of space with no path between them. In this view, geometry is not a stage on which quantum events happen. Geometry is what quantum entanglement looks like when you stand back far enough. This is a beautiful guess. It is not yet a proven theory. The mathematics works in certain simplified model universes, the kind physicists build on paper to test ideas. Whether the same picture holds in our own universe is an open question. Still, the hint is striking. For decades, gravity and the quantum world seem to speak past each other. Now, a single phenomenon, entanglement, may sit at the meeting point of both. Other researchers see it differently. They argue that entanglement is a feature of quantum systems living inside spacetime, not the source of spacetime itself. In this competing view, space comes first, and the quantum links are just one of the many things that can happen within it. Both pictures fit much of what we observe. Neither one has been ruled out. The question of which comes first, the stage or the connections, remains unsettled. The connections do not stop at small scales. Black holes, those silent collapsed stars, seem to be tied to entanglement in ways no one fully understands. The radiation that slowly leaks from a black hole appears to carry quantum links back to the matter that fell inside long ago. Some thinkers have proposed that the inside and the outside of a black hole are connected by tiny bridges in space, bridges built from entanglement itself. These bridges, if they exist, would never let anything travel through them. They would simply be the geometric echo of a quantum link. This idea reaches further still. If entanglement and geometry are two faces of the same thing, then the gravity that binds galaxies, the curve of space around a star, air, and the spread of the early universe might all be quiet expressions of a deeper quantum web. Gravity would not be a separate force layered on top of the quantum world. It would be a pattern that emerges when enough quantum pieces are linked in just the right way. There are reasons to be careful. The mathematics that supports these ideas often lives in universes with strange shapes, universes that bend inward in ways ours does not seem to. Translating the results into our own cosmos is hard, slow work. Some researchers think the translation will eventually succeed. Others suspect that entanglement, while beautiful, will turn out to be only one ingredient in a recipe we have not yet written down. What makes this line of thought so quietly thrilling is its scope. A single idea, born from experiments on pairs of photons in small laboratories, may stretch all the way out to the shape of the cosmos. The same threads that link two particles on a table might, in some unfinished way, link the rooms of the universe itself. If so, then every distance you have ever measured, every gap between two stars, Every patch of empty sky would be a record of countless tiny connections holding the world in place. Whether that picture is true or only a lovely shadow of something truer still, no one yet knows. Our picture of how forces work has shifted slowly over the past 100 years, like sand moving under a quiet tide. In the early days of physics, forces were thought of as invisible pulls reaching across empty space. Then, piece by piece, that idea changed. Physicists began to describe forces not as pulls, but as exchanges. Tiny messenger particles passed between objects, carrying influence from one to the other. Light became a stream of photons. The forces inside the atom found their own carriers, too small to see directly, but real enough to leave traces in our finest experiments. That slow change in thinking raised a quiet question that still has no answer. If 3 of the 4 fundamental forces in nature are carried by particles, then gravity should have one as well. Physicists gave this imagined particle a name long before they ever saw a sign of it. They called it the graviton. It would be massless, traveling at the speed of light, and it would weave the gentle pull we feel between every object in the universe. The idea is simple enough to say in a single breath. Finding the particle is another matter entirely. The graviton, if it exists, would interact with the rest of reality far more weakly than any other known messenger. To detect a single one, some calculations suggest you might need a detector the size of a planet, placed in orbit around a neutron star and waiting patiently for longer than the current age of the universe. The numbers stretch the imagination. They also explain why, after nearly a century of searching, the graviton remains a hypothesis rather than a discovery. Yet the search has changed in ways earlier physicists could not have guessed. 100 years ago, gravity was studied mostly through the slow turning of planets and the bending of starlight near the sun. Today, enormous instruments listen for gravitational waves, the soft ripples in space-time, made when massive objects collide far away. These waves are predicted by general relativity, and they have been measured. Each ripple, in principle, should be made of countless gravitons flowing together, the way a beam of light is made of countless photons. We can hear the wave. We cannot yet pick out a single particle from within it. This is where the old tension returns. General relativity treats gravity as the curving of smooth space-time, with no need for any particle at all. Quantum mechanics treats every other force as a shower of small messengers. If gravity is truly a force like the others, the gravity is something different, something woven into the geometry of space itself, then perhaps no such particle is needed. Both views have careful supporters. Neither has been ruled out. Some researchers wonder whether the graviton, if real, might leave gentler clues than a direct detection. They look for tiny departures from Einstein's predictions in the way gravitational waves travel across the cosmos. A graviton, with even the slightest mass, would cause waves of different frequencies to arrive at slightly different times. So far, no such delay has been found, and the measurements grow more precise with each new event the detectors record. The silence is itself a kind of answer, narrowing the space where the particle might hide. Other researchers take a different path entirely. They suggest that gravity may be what physicists call an emergent force, something that looks like a fundamental interaction at our scale, but arises from deeper patterns at the smallest scales. In that picture, asking for a graviton might be like asking for a particle that carries the pressure of a gas. Pressure is real. You can feel it, but it is not carried by a messenger. It emerges from the motions of countless tiny pieces. Gravity, in this view, might be the same kind of soft collective effect. The picture keeps shifting. New instruments come online every few years, each one a little more sensitive than the last. Tabletop experiments now try to test whether very small masses can become entangled through their gravitational pull alone. If they can, that would hint that gravity itself follows quantum rules, and the graviton's case grows a little stronger. If they cannot, the older idea of smooth, classical space-time gains quiet ground. So the long search continues, slowly, patiently, with no certainty about what it will find. Generations of physicists have asked the same question and handed it forward, a little sharper each time. The graviton may be discovered in your lifetime. It may never be discovered at all. For now, it sits between possibility and proof. A particle imagined but not yet met, drifting somewhere in the space between two great theories that still refuse to fully speak the same language. Light is the messenger we trust most. It carries word from places no ship could ever reach, across the vast arc between galaxies. Light slips through unbothered, holding its colors and its rhythms steady. We have learned to read those colors the way an old sailor reads the sky. The faint red glow of hydrogen, the cooler blue of hot young stars, the gold orange of an aging sun cooling into its long evening. In nearly every corner of physics, light has been the key that opened the lock. It showed us the bending of space around the sun during an eclipse. When starlight curved as it slipped past the bright edge, it revealed the cosmic background, that soft glow left over from the universe's first warm breath. It carries the fingerprints of distant atoms, telling us what stars are made of from millions of light years away. When it comes to the scene between gravity and the quantum world, light goes strangely quiet. The mystery hides in a place too small for any beam to reach, and too gentle to leave a clear mark. Imagine trying to photograph the surface of a calm lake by throwing boulders into it. The boulders are the only tool you have, but each one shatters the very surface you wanted to see. This is the trouble physicists face at the smallest scales. To peer down to the Planck length, the level where space itself may become brainy, you would need light of such fierce energy that it would warp the region you were trying to study. The light becomes the boulder. The picture is gone before it forms. So the deepest scales remain dark to us, not because no light exists there, but because no light we can send is gentle enough to leave them undisturbed. Even so, experimenters keep looking, patient and clever. Some watch the sky for faint hints that space itself might have a texture. If space-time is woven from tiny grains, then very high-energy photons, the most piercing kind of light, born in distant cosmic blasts, might travel at slightly different speeds, depending on their color. Over billions of years of flight, even the smallest difference would stretch into a noticeable lag. So far, the light has arrived together, color by color, smooth and even. The grains, if they exist, are hiding well below the reach of present tools. Another set of searches turns to the soft glow left over from the early universe. That ancient light, cooled now to a whisper of microwaves, carries gentle ripples within it. Some researchers wonder whether quantum gravity might have left a faint signature on those ripples, a particular twist in the way the light is polarized. One possibility is that a sea of primordial gravitational waves stirred the early plasma and pressed a soft pattern into the glow. Another view holds that any such pattern would be too faint to ever lift out from the noise of the foreground stars and dust. The hunt continues. The pattern so far has not appeared. There are also quieter experiments tucked into vibration-proof rooms here on Earth. Inside them, beams of laser light bounce between mirrors hanging on the finest of threads. The hope is to watch a small object held in two places at once, in a true quantum overlap, and see whether its own tiny gravity behaves quantum-like as well. If it does, that would be the first soft glimmer that gravity itself follows quantum rules. If it does not, the puzzle deepens. The mirrors must be kept colder than the cold of deep space, shielded from every footstep, every passing truck. The signal, should it come, will be smaller than the trembling of a single atom. Light, then, plays a strange role in this mystery. It is our finest tool and our most stubborn limit. It carries word from the births and deaths of stars, from the swirling edges of black holes, from the faint warm shadow of the beginning. Yet, at the very seam where the two great theories meet, light grows shy. The energies needed to see clearly would themselves change what is seen. Perhaps a future telescope, sensitive in ways we cannot yet build, will catch the first faint shimmer of quantum space-time in the color of an old gamma-ray burst. Perhaps a tabletop mirror will tremble in a pattern no classical theory can explain. Perhaps the answer will come from a direction nobody is presently watching, slipping into view from the side. For now, the deepest light we can gather tells us mostly this: the universe at its smallest still keeps its own counsel, and we sit, quiet observers, waiting for a glow we have not yet learned to see. Space, as you may have heard, is mostly silent. Sound needs something to travel through, and the vacuum between stars is too thin to carry it. Yet, the universe is still full of vibration. Magnetic fields ripple, plasma hums, gravity itself bends and stretches space in slow waves. When scientists turn these signals into audio, the cosmos begins to sing in its own quiet voice. And inside that song, there is one steady note no one fully understands. That note is the cosmological constant. It is a small number tucked into the equations of general relativity. Einstein first added it almost by accident, then removed it. Then later, it was put back when astronomers found something strange. The universe is not just expanding, it is expanding faster and faster. Some unseen pressure seems to be pushing space itself outward, gently, everywhere, all at once. If you could listen to this pressure, it would not be a roar. It would be more like a low, even tone, holding steady across billions of years. Galaxies drift apart on its breath. The night sky grows slowly emptier. And the strange thing is, no one knows where this tone comes from. Quantum mechanics offers a guess: empty space. In the quantum view is never truly empty. The vacuum hums with tiny fluctuations, brief flickers of energy that appear and vanish too quickly to catch. When physicists try to add up all these flickers, they get a number for how much energy the vacuum should hold. That number, in theory, should drive the expansion of space, so they compare the prediction to the measurement. And here, the song falls out of tune. The quantum calculation gives a value that is far too large. Not twice too large, not 1,000 times too large. By some estimates, the quantum prediction is around 120 orders of magnitude larger than what the universe actually shows. That is a 1 followed by 120 zeros, sitting between theory and reality. It is often called the worst prediction in the history of physics. Something is deeply wrong, and no one is sure what. One possibility is that the quantum fluctuations mostly cancel each other out, leaving only a tiny remainder. But for that cancellation to work, the numbers would need to balance with almost impossible precision. Some researchers find this too neat to believe and look for a hidden reason behind it. Another possibility is that the cosmological constant is not constant at all. It may be a slowly changing field, sometimes called quintessence, drifting in value over cosmic time. If that is true, the steady tone is not really steady. It bends, very slowly, like a long note slipping from one pitch to another over billions of years. So far, observations have not pinned this down. The expansion looks smooth, but the data still leaves room for a gentle drift. A third idea moves in the opposite direction. Maybe the cosmological constant takes different values in different regions of a much larger multiverse, and we simply live in one of the few places where it is small enough for galaxies and stars to form. In this view, the small number is not explained. It is just selected, the way a quiet room is selected by someone seeking quiet. Many physicists find this answer unsatisfying. Others find it the only honest reply we have so far. Beneath all these guesses sits the same old gap. General relativity treats the vacuum as a smooth background. Quantum mechanics treats it as a churning sea. When you ask both theories what empty space weighs, they answer in completely different languages, and their numbers do not meet. There is a poetic side to this. The accelerating expansion can be translated into sound through analogy. Imagine a slow, sustained chord, barely changing, filling every corner of the cosmos. Layered on top are the quick chirps of merging black holes, detected as gravitational waves and turned into audio by careful instruments. Those chirps last only a heartbeat. The chord beneath them has been holding for almost 14 billion years. Listening this way, you can almost feel the shape of the mystery. The quick notes belong to general relativity, clean and geometric. The deep hum belongs in some way to the quantum vacuum, and the math that should let one explain. The other has not yet been written. For tonight, it is enough to picture this, a vast dark space, very gently stretching, galaxies drifting outward like sparks on a slow wind, a single turn running underneath it all, far below human hearing, holding the universe open, and somewhere inside that tone, a number so small and so strange that it has quietly defeated the cleverest equations we have ever built. When mathematicians first began searching for a bridge between gravity and the quantum world, they ran into a strange and beautiful clue. The equations seemed to work better if space had more dimensions than the three we can see. Not more rooms or more places, but more directions woven into the fabric of every point. The idea felt impossible at first, and yet the math kept whispering it back, again and again. We know 3 dimensions through our bodies. We can step forward, step sideways, and step up, add time, and we have 4. But certain versions of string theory only balance their equations when space carries 6 or 7 extra dimensions, hidden somehow within the ordinary world. These would not be faraway places. They would be folded so tightly into each point of space that no instrument has ever felt them. One picture of this folding comes from a shape with a soft poetic name. It is called a Calabi-Yau manifold. Picture a tiny curled flower at every location in the room around you. Each petal turns inward in a precise way, the curves never crossing, the surfaces never tearing. The geometry is gentle but exact. The math demands a smoothness that only certain shapes can hold. The beauty here is hard to overstate. The equations do not allow just any shape. They allow a small family of forms, each one balanced like a perfect crystal. The numbers that describe their curves connect to the numbers that describe particle masses, charges, and the way forces behave. If this picture is right, the properties of every electron and quark would echo the geometry of a shape too small to ever see. Some researchers find this idea deeply appealing. The universe would run on quiet rules, where what we call physics is really hidden geometry expressing itself in the open. A vibration along one of those curled directions could appear to us as a particle. A twist could appear as a force. The cosmos would be playing a kind of silent music on strings too small to imagine, and the notes would be the matter we are made of. Other researchers are not convinced. The trouble is that the math allows an enormous number of possible shapes. Some estimates suggest more arrangements than there are atoms in the observable universe. Each shape would give a slightly different physics. Without a way to pick which shape matches our world, the elegance starts to blur. The theory becomes a vast catalogue rather than a single answer. The question of why we live in this universe and not another stays just as open as before. Other approaches to quantum gravity avoid extra dimensions entirely. Loop quantum gravity, for example, keeps space to 3 dimensions but breaks it into tiny woven loops. Causal dynamical triangulations build spacetime out of small flat pieces that glue together like a quilt of triangles in 4 dimensions. In these pictures, the hidden mathematics is not in extra directions, but in the rules that decide how the pieces connect. Both frameworks chase the same goal through very different geometry. What is striking is how often simple numbers reappear in all of these approaches. The square root of 2, the ratio of a circle to its diameter, the constants that govern how light travels and how particles behave. These numbers do not change between theories. They sit at the base of every attempt, like quiet anchors. Whatever the deeper framework turns out to be, it will almost certainly honor the same elegant ratios that have appeared in physics for centuries. There is also the Planck length, that smallest meaningful distance, about 16 zeros after the decimal point in meters. Below that scale, the very idea of distance may stop making sense. The math of hidden dimensions, of woven loops, of triangulated quilts, all begin to matter most near this scale. It is the edge where the equations of the smooth universe and the equations of the grainy one finally have to agree, or finally give way to something neither of them has yet described. For now, the hidden geometry remains a guess, dressed in beautiful math. No experiment has confirmed that extra dimensions exist. No experiment has ruled them out. The shapes proposed by theorists are testable in only the most indirect ways, through subtle effects on particles at high energies, or through the patterns of cosmic light from the early universe. Each year brings tighter limits, but no clear answer. The geometry stays quiet. What the mathematics offers, even without a verdict, is a sense that the universe might be simpler than it looks. Not simple in the everyday sense, but simple at its heart. A few rules, a few shapes, a few numbers, generating everything we see. Whether that simplicity lives in extra dimensions, in woven loops, or in something not yet imagined, remains a question still waiting in the dark. There is a quiet idea moving through modern physics, one that asks us to look at space-time in an entirely new way. It suggests that the smooth fabric we know, the gentle continuum that holds planets and light and time itself, may not be fundamental at all. It may be something that emerges, the way the surface of a calm lake emerges from countless invisible water molecules. From far away, the lake looks like a single sheet of silver. Step closer, and the sheet dissolves into trembling drops, each one moving on its own. If this idea holds, then space and time are not the bottom layer of reality. They are a pattern that appears when something deeper organizes itself, just so, and the deeper something might not look like space at all. It might look like a vast web of relationships, a network of information, a kind of quiet bookkeeping that the universe performs beneath the surface of every star and every breath. Some researchers wonder whether this hidden layer is built from tiny pieces, almost like pixels on a screen. Zoom in far enough on a photograph, and the smooth colors break into small squares. Zoom in far enough on space, the thinking goes, and the smoothness of space-time might break into discrete units. These would not be pixels of light, but pixels of geometry itself, each one too small to see, too small to ever touch with any tool we have built or imagined. The size of these possible pixels would be the Planck length, a scale so tiny that a single atom looms over it like a galaxy looms over a grain of sand. At that level, the very notions of here and there, before and after, may begin to blur. One possibility is that space-time simply ends, replaced by something stranger. Another possibility is that it never began in the way we picture it, and that smoothness is only ever a long-distance illusion. The balance required for this to all hold together is hard to imagine. The pixels, if they exist, must be arranged in such a way that the world above them looks perfectly continuous. Every motion of a planet, every ripple of a gravitational wave, every shimmer of light across a billion years must average out from these tiny pieces without revealing the seams. If the underlying structure were even slightly different, the smooth sky we know might flicker, or twist, or fail to form at all. There are competing pictures of how this might work. In one view, space-time emerges from entanglement, from the way countless quantum systems share their fates across the void. Pull one thread of entanglement, and a small piece of geometry comes with it. Cut enough threads, and space itself would unravel into something we have no word for. In another view, space-time emerges from networks of relationships between simple, abstract elements, where distance is not a given, but a calculation, an answer the universe arrives at by counting connections. Neither picture is proven. Both are mathematical sketches, drawn in the hope that one day they will match something real. Some researchers find the emergent view beautiful, almost inevitable. Others suspect that space-time is fundamental after all, and that the deeper layer we keep searching for is a mirage cast by the limits of our equations. What makes the question so delicate is that the world we live in seems tuned to a remarkable degree. The strength of gravity, the masses of particles, the smoothness of the early universe, all sit within narrow ranges that allow stars to form, planets to cool, and atmospheres to settle into thin protective veils. Earth itself rests at a careful distance from a steady star, wrapped in a layer of air no thicker than the skin on an apple, compared to the planet beneath it. Change any of these numbers by a little, and the calm we enjoy might never have appeared. If space-time is emergent, then this calm rests on an even more fragile foundation, the smoothness that lets light travel cleanly across galaxies, the steady flow of time that lets a candle burn down at a predictable rate, the very stage on which atoms perform their patient work would all depend on the quiet cooperation of countless hidden pieces we cannot see, cannot reach, and cannot yet describe with confidence. It is a strange thought to carry into the dark. The ground beneath the night sky may be woven from something that is not ground at all. The wide and steady cosmos may be a surface, beautiful and trustworthy, floating above a depth that no instrument has yet found. Whether that depth is real, and whether it has pixels, and whether our smooth world is its quiet song, remains an open question. We can only sit with it gently and wonder. Time moves forward. That much feels obvious. A cup falls and shatters on the floor. The pieces never gather themselves back into a cup. A star burns its fuel and slowly fades. It does not unburn. Cream stirred into coffee will not unstir. The future looks different from the past, and the difference feels as solid as the ground beneath our feet. Yet, when scientists look at the deepest equations of physics, this forward motion almost vanishes. The laws that govern particles, the laws that govern gravity, the laws that govern light, almost all of them work just as well running backward as forward. There is no built-in arrow. The math does not care which way the clock turns. A film of 2 billiard balls colliding looks just as valid played in reverse. So where does the arrow come from? Why does the universe feel so deeply directional when its rules do not seem to insist on it? The standard answer points to entropy. Entropy is a measure of disorder, of how many ways the pieces of a system can be arranged without changing its overall look. A neat stack of cards has low entropy. A shuffled deck has high entropy. The universe, scientists believe, began in a state of remarkably low entropy and has been drifting toward higher entropy ever since. The arrow of time, in this view, is the slow spreading of order into disorder. But this answer raises a deeper question. Why did the universe begin in such an orderly state to begin with? No one knows. The initial conditions of the cosmos remain one of the quietest mysteries in physics. Some researchers wonder if there is a deeper law that forced the early universe into low entropy. Others suspect it may simply be a feature we will never explain, only accept. The riddle grows stranger when quantum mechanics enters the room. In the quantum world, particles do not have definite properties until they are measured. A particle can be in many states at once, a soft cloud of possibilities, until something interacts with it, and the cloud collapses into a single outcome. This collapse seems to carry its own arrow. Once a measurement happens, it cannot be undone. The cloud does not reassemble. The possibilities do not return. No one fully agrees on what this collapse is, or whether it is even real. One view holds that measurement is a fundamental process, a genuine break in the quantum story. Another view, sometimes called the many worlds idea, suggests that nothing ever truly collapses. Instead, every possible outcome happens, each in its own branch of reality, and we only ever see one. In that picture, the arrow of time becomes the way each branch remembers its own past, while losing track of the others. A third group of researchers wonders if time itself might be an illusion at the deepest level. Certain equations of quantum gravity, when written down carefully, contain no time variable at all. Time simply drops out. What remains is a frozen mathematical structure, timeless and still. From inside this structure, observers like us would experience the flow of moments because of how information is woven between different parts of the system. Time would not be a river the universe floats down. It would be a story the universe tells itself from within. These ideas remain speculative. The mathematics is unfinished. The experiments to test them may not exist for generations, if they ever exist at all. Yet the puzzle is rich enough to keep many of the best minds in physics quietly working through long evenings. They are trying to understand how the smooth, directional time of our daily life emerges from rules that do not seem to need a direction. Black holes deepen the riddle further. When matter falls in, information about it appears to vanish behind the event horizon, the invisible edge past which nothing can return. But quantum mechanics insists that information can never truly be lost. The two ideas clash, and the arrow of time gets caught in the middle. Some theories suggest that the information slowly leaks back out in faint radiation. Others suggest it is stored in subtle correlations we do not yet know how to read. The full picture is still missing, so the arrow of time sits at the crossroads of every unsolved question in physics. It touches the beginning of the universe. It touches the collapse of quantum possibilities. It touches the strange silence inside black holes. It touches the missing theory that would bind gravity and quantum mechanics together. And it touches the small, ordinary moments of our lives, where cups break and stars fade, and cream swirls into coffee, reminding us that something about reality is moving, even if we do not yet understand what. At the heart of every black hole, the equations of general relativity reach a place they cannot describe. The math tells us that matter falls inward and inward until density becomes infinite and curvature becomes infinite, and the formulas simply stop making sense. We call this place a singularity. The word sounds precise, but it is really a kind of confession. It marks the spot where our finest theory of gravity admits that it does not know what happens next. Quantum mechanics has its own version of this confession. When physicists try to apply its rules to the singularity, the answers come back as infinities too, stacked on infinities, with no clean way to subtract them. Two great theories arrive at the same hidden door, and neither one has the key. So the question of what truly sits at the center of a black hole remains genuinely open. Some researchers think there is no singularity at all, only a region of extreme but finite density that quantum gravity would tame. Others think the singularity is real, and that our theories simply lose their voice in its presence. Looking forward in time, this puzzle will not stay still. Black holes themselves are slowly changing. According to one widely studied idea, first proposed in the 1970s, black holes give off a faint glow of radiation and very slowly lose mass. If that idea is correct, then on timescales far longer than the current age of the universe, even the largest black holes will shrink. Their cores, hidden behind their horizons for now, will draw closer to the outside world. What happens in the final moments of a shrinking black hole is one of the most contested questions in physics. One possibility is a quiet fading. Another is a small final burst. Another is that something stable and strange remains behind. A tiny remnant carrying the memory of everything the black hole once swallowed. A million years from now, the night sky will look much as it does tonight. The constellations will have drifted a little. A few familiar stars will have ended their lives, and new ones will have been born inside glowing clouds of gas and dust. The deep questions about singularities will likely still be open, though our instruments may be far more sensitive. Perhaps, by then, gentle tabletop experiments will have caught the faintest whisper of quantum gravity, a tiny shimmer in the entanglement between two small masses that hints at how space-time behaves when it is forced to be quantum. A billion years from now, the picture changes more dramatically. Our sun will have swollen into a red giant, swallowing its inner planets and scorching the rest. Earth, if it still exists in some altered form, will no longer hold its oceans, but the Milky Way and its neighbor, the Andromeda Galaxy, will be drifting toward one another, beginning a long, slow merger that will reshape the night sky over hundreds of millions of years. New stars will ignite in the turbulence. New black holes will form. New singularities, if that word still applies, will be born inside them. The mystery of what lies at their hearts will be passed forward again and again to whatever minds are there to ask. Further still, on timescales of trillions of years, the last bright stars will fade. The universe will grow dim and cold. Black holes will become the dominant features of the cosmos, slowly evaporating across spans of time so vast that the numbers stop feeling like numbers. And yet, even in that distant quiet, the question we are asking tonight may still not be settled. The bridge between space-time and quantum mechanics may have been built, or it may have been replaced by something stranger, or it may still be a sketch on a chalkboard somewhere. waiting. There is a humility in all of this. The singularity reminds us that knowledge has edges. Not every question we can ask has an answer we can reach with the tools we have today. Some researchers find this troubling. Others find it beautiful. They see the singularity not as a wall, but as an invitation, a sign that the universe still has secrets large enough to humble its cleverest observers. For now, the limits of knowing are also the limits of imagining. We can write equations up to a point. We can sketch theories beyond that point and test the ones we can. The center of the black hole stays dark to us, not only because no light escapes, but because our deepest ideas have not yet learned how to speak there. The future of this mystery is long and patient and quiet, and almost certainly full of surprises we cannot yet picture from where we stand tonight. Step back now, as far as the mind can go, and look at the whole picture from a great, quiet distance. There is a small world turning in the dark. On that world, soft creatures made of star ash are trying to understand the rules that built them. The calcium in their bones was forged in dying stars. The iron in their blood was scattered by ancient explosions. They are listening to the universe with instruments they grew from its own dust, and they are asking it to explain itself. This is the strange and tender thing about the search for quantum gravity. It is not happening somewhere far away. It is happening inside the very atoms that make up the people doing the asking. Every thought about the Planck scale rides on neurons that obey both quantum rules and the soft pull of gravity. Every equation is written by a hand that lives at once in both worlds. The mystery we have been sitting with all night is not external. It runs straight through us. For nearly a century, the brightest minds in physics have stared into this gap and offered their best guesses. Some have spent whole lifetimes shaping the mathematics of vibrating strings. Others have spent decades weaving the loops of quantum geometry. Some have proposed that spacetime is a hologram. Some have proposed it is a kind of foam. Some have proposed it is woven from threads of entanglement. Some have proposed it does not really exist at all, and that what we call space is just the shape of relationships between deeper things we have not yet named. None of these ideas has yet won. None has yet been ruled out. They sit side by side in the dark, each carrying a piece of the puzzle, none holding the whole. There is something humbling in that picture. We have built telescopes that see light from the edge of the visible universe. We have mapped the cosmic background radiation across the entire sky. We have detected the ripples of gravitational waves from black holes that collided more than 1 billion years ago. We have measured the mass of the electron to a precision so fine it almost defies belief. And yet, when we ask the simple question of what space and time actually are, the universe falls quiet. It hands us 2 beautiful theories and refuses to tell us how they fit together. Perhaps that quiet is the most honest answer the universe can give. Perhaps the question itself is still half-formed, waiting for a way of thinking we have not yet invented. The history of physics is full of moments when an old puzzle dissolved because someone learned to ask it in a new language. The orbit of Mercury did not make sense until space-time itself could bend. The flicker of certain metals in light did not make sense until energy came in small packets. Each time, the universe was not stubborn. It was patient. It was waiting for us to grow into the question. Maybe quantum gravity is waiting in the same way. Maybe somewhere in a quiet room, on this world or another, someone is about to think a thought that changes everything. Or maybe the answer will take centuries. Maybe it will take longer than our species has existed so far. The universe is in no hurry. It has all the time there is. There is comfort in that, if you let it settle. The mystery is not a failure. It is a sign that the cosmos is deeper than our current tools can reach. It means there is still more to find. The story is not finished. The book of physics has open pages near the end, and no one yet knows what will be written there. You are part of that story, in a small and quiet way. The atoms in your body were assembled in the heart of stars and scattered across light years before they gathered into you. They have been part of nebulae and oceans and ancient stones. Tonight, they are arranged into a person, lying in a soft bed, wondering about the shape of space-time. Tomorrow, they will still be wondering, in some form, somewhere, for as long as the universe keeps making minds. It is a beautiful thing to be a small piece of the cosmos that has learned to ask about itself. It is a beautiful thing to live in a moment when so much is still unknown. The dark above us is not empty. It is full of theories still waiting to be tested, full of questions still waiting to be asked, full of answers still waiting to be heard. And we, made of starlight and patience, are the listeners. We are the part of the universe that wanders. And so we come to the end of our long, slow walk through one of the deepest puzzles in all of science. We have spent hours together with a question that no one on Earth can yet answer. Two great theories, two beautiful languages, one universe that somehow speaks both at once, without telling us how. There is something gentle about ending here, not with an answer, but with a quiet acceptance that the picture is still being drawn. Somewhere tonight, in offices and libraries and quiet kitchens, people are working on this puzzle. They are filling chalkboards with symbols. They are running numbers through long, patient machines. They are sitting in the dark, much like you, wondering how it all fits together. The work goes on, slow and steady, the way water shapes stone. And the universe, for its part, does not seem in any hurry to explain itself. It simply keeps doing what it has always done. Galaxies turn in slow, silent wheels. Stars are born inside soft clouds of dust. Planets drift in long, looping paths around their suns. None of them are waiting for us to solve the math. They simply are. Picture, for a moment, a small blue world resting in the dark. Its oceans are calm tonight. A thin sheet of moonlight lies across the water like a sheet of silver silk. Clouds move slowly above the sea. Somewhere on a quiet shore, waves fold themselves onto the sand and pull back again the way they have for billions of years. The same forces we have been talking about are at work there. Gravity is holding the water to the world. Quantum fields are humming inside every grain of sand. The two great theories are dancing together in the smallest droplet of foam, even though no one has yet written down the music. Lift your view a little. See the planet from above, a soft round shape glowing faintly against the deep black. See the gentle curve of its edge. See the slow turn of its weather. Now lift further. See the moon nearby, pale and pocked and patient. See the sun far off, pouring out its quiet warmth. See the other worlds of the system, each one rolling along its slow path, each one tied to the others by the smooth pull of space-time. None of them are afraid of the unfinished picture. They are simply part of it. Lift further still. See the galaxy spread out in a long, slow spiral, its arms full of stars too many to count. See how it turns, taking hundreds of millions of years for a single round. See how it sits among other galaxies, each one a small island of light in a great dark sea. Somewhere inside all of that, the same two theories are still at work. Smooth space, bending under great weights, tiny particles flickering in and out of being. The bridge between them is still hidden, still waiting, still patient. There is comfort in being small inside something so large. The questions we have walked through tonight are not problems to be solved before sleep. They are simply part of the shape of the world. The mystery does not need you to fix it. The universe does not need you to finish its math. It is enough to know that the question is there. It is enough to feel the quiet weight of it. It is enough to rest. We may live to see this puzzle solved. New experiments are being built. New ideas are being tested. New minds are being trained, year by year, to look at the problem in ways no one has tried before. Or we may not. The bridge may take another century. It may take longer. It may turn out to look nothing like what anyone has guessed so far. That is part of the beauty of the work. The ending is not yet written. For now, let the question rest beside you, like a stone smoothed by water. Let the soft turning of galaxies become the rhythm of your breath. Let the silent humming of quantum fields become the hush behind your thoughts. The universe is vast and gentle and old. It has held everything that has ever lived. It is holding you now. Thank you for spending this quiet night with me. Thank you for letting your mind wander out into the dark with mine. Whatever the answer turns out to be, the wandering itself is a kind of small, warm gift. Carry it with you into sleep. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.